Okay. So this is where already. What I have done since yesterday is add an actual observational plot. This is from Anderson et al. 2023. And what it's plotting is the random velocity in the z direction of stars at in different radial bins. The blue bin, this is for 3 to 5 kiloparsecs, and these curves here are for much larger, 11 to 13 kiloparsecs, etc. So different radii. And what you're seeing is a very nice increase in random velocity as a function of age. And that's the empirical evidence that fluctuations in the gravitational potential cause stars to gradually increase their actions. So there is diffusion in phase space. And the diffusion happens, not surprisingly, fastest at small radii, where the dynamical time is shortest. I guess it's slightly interesting that the diffusion rate doesn't increase so strongly. Anyway, yes. All right, so fluctuations in the potential are causing stars to do a random walk. On the back of an envelope, you can persuade yourself, and people did persuade themselves a very long time ago, that the fluctuations in the potential due to individual stars are insignificant in this context. Stars are moving so fast, they have random velocities which are so large, and the stellar density is so low that they just don't come close enough to each other that their scattering off each other does anything very much. What is doing the scattering is fluctuations in the potential that are collective in nature, which are caused by overdensities, dark matter, overdensities of macroscopic overdensities of stars. So we're going to try and understand this by saying that the distribution function is equal to a sum of a distribution function f naught, which depends only on the current actions, and a fluctuating part, which is caused by the fact that the potential, when I say the current actions, that is some set of actions which are not the angle action coordinates of the actual fluctuating potential, they're the angle action coordinates of some imaginary underlying smooth, barely changing, but very, very slowly changing potential. And this fluctuating term that will have in the potential, which will average nothing. And so, and we're dealing with a collisionless system. So we argue that the collisionless Boltzmann equation says this. We put in F is equal to F naught plus F1. We expand this and we arrive down here clearly. And now we say, so there's a second order term, a first order term, a first order term, a first order term, and a term which we will persuade ourselves is small because, well, what we're going to do now is time average. If you take the time average of this is going to disappear, this is going to disappear, and this is going to disappear because those are the fluctuating parts, which by definition average to zero. Perhaps I should have said ensemble average. And so what survives the averaging is this and this. So we say the rate of change of the sort of underlying distribution function is the expectation value of this product of two fluctuating things, which does not vanish because these two things are correlated with each other. But H1, the perturbation in the Hamiltonian, is simply the perturbation in the potential. So we have this. And then we can go back to the original equation and say that, well, we can subtract this from the original equation. And if we neglect this minus this, right? So if we neglect the difference between the second order fluctuating quantity and its average, then we conclude that F1 satisfies this equation. So that's the basis on which I'm going to proceed. We could indeed spend some time discussing whether it's the right thing to neglect this, but I think it's fair to say that the difference between these two is surely small compared to these first order fluctuating things. So that's what we're going to discuss. And if we expand F and phi 1, the two fluctuating things in angle action coordinates, as we always do. So phi 1 is this sum of Fourier terms, and F1 is a corresponding sum of Fourier terms. Then we can stick that, we can work out what this is, the Poisson bracket, because this is d by d theta, d by dj minus d by dj, d by d theta. So that's, and you know how to do the d by d thetas because we've expressed everything in angle action coordinates. So this ik comes from differentiating the exponentials. The differential with respect to actions is left alone. So trivially that. And now we can, it turns out that we can take the d by dj out of this, right? Right out, because in taking it out, we generate some additional terms which cancel on each other between these two terms here, so that d by dj of the expectation of this product is the same as this. So I think I may have pointed this equation yesterday. This is well, this comes down to here. This derivative, this divergent, which is taking the divergence of a 3x3 matrix at the end of the day. It's saying that stars are conserved. The rate of change of the stars at some point in action space is minus the divergence of the flux of stars through action space, and the flux of stars through action space is given by this expectation value, which doesn't value only because there is causal connection between f and phi. And as I said yesterday, the causal connection is twofold. On the one hand, a fluctuating potential steers stars. It changes the orbits of stars and causes a fluctuating component in the distribution function through dynamics. And also, a fluctuating distribution function leads to a fluctuating density, which through Poisson's equation gives rise to a fluctuating this. So these two are causally connected, and that's why that correlation doesn't vanish. Now we will go back to that formalism and equation, but first I want to discuss this phenomenon of diffusion in a different way, the Fokker-Planck route. So what we say is, let's consider the number of stars that there are in d cubed j. The number of stars in d cubed j, or the mass or whatever, is equal to the density of stars there, integrated over all angles associated with that. That's where the 2 pi cube comes from, times the small piece of volume d cubed j. So that's the number of stars in there. The rate at which they leave is given by this integral. We're going to so p of j and delta is the probability per unit time that a star with actions j suffers a change in its actions delta. So j is a vector, delta is a vector, moving to j plus delta, right? So when I integrate over all possible changes, this probability density, this probability per unit time, I get the rate per unit time at which stars move out of this volume d cubed j. Of course, stars are moving into that volume because they start off at, shall we say, j minus delta, and at a rate p j minus delta delta, they suffer a change in actions delta, which moves them into j, right? So this is the probability per unit time. Well, no, that doesn't kind of work. But if I now multiply this by the volume, this is going to give me the rate at which stars coming from somewhere else move in there. And now by conservation of stars, I can say that the rate of change of the distribution function times the phase space volume associated with d cubed j, the 2 pi cubed coming from the integral over thetas, is equal to the difference between the rate at which they come in and the rate at which they go out. And now we Taylor expand, we argue that the deltas are probably very, very small, right? That's in fact the key approximation we're making. We're saying that the reason this is a diffusion process, what is happening is that stars are experiencing a very large number of random adjustments, small random adjustments to their actions. So the deltas, this probability is significant only when delta is small, and f is not a very steeply varying function of j. And we don't think this probability of being kicked out of there is that rapidly varying either. So it should be okay to expand this product on their first arguments. So we Taylor expand this product perfectly trivial Taylor expansion, and plug this in here, and you can imagine that this kills that term in the expansion, and we're left with just these two terms here. And then we say that we can move this integral over delta. The only things depending on delta now are p and that. So we can do this integration over the p, calling this delta I bar of j. So that's the mean change, that's the mean change in delta per unit time at actions j, and this thing is sort of more or less the mean square change in actions per unit time, and then we come down here, right? Because we've done the integral and we've got the derivatives and so on and so forth. So this we now need, yes, okay. So the flux is clearly minus what we're taking the divergence of on the right hand side. And what it's but we want now to break this into a part which is proportional to f and a part which is proportional to the gradient of f. So that's what we do. And so we have a first order diffusion coefficient, which is this part of it we've already got there, and the other part we get from when we differentiate this and leave f alone. And then we've got the other part which comes from when we sorry, I'm missing a derivative thing here, am I not? What's happened to that? Right. So this should be d by dj of delta squared, right? The part that we get when we leave. No, sorry, no, that is correct. Excuse me. Yes. Sorry, that is correct. It's the part that we get when we're differentiating the f and the delta squared just stands by. All right, so that's established that we've got a first order diffusion coefficient and a second order diffusion coefficient, and I kind of explained, I hope yesterday, that we need both of these, but for the conservation of energy. This term tends to cause stars to diffuse to very large actions, which means very large energies, requires energy. If we're dealing the scattering process in most contexts would happen at more or less constant total energy, and so we need this term to drag things back. This is typically going to be a negative number. Okay, so so now we want to compute these things basically by computing the deltas. So we have that j dot, of course, is minus dh by d theta, which is minus d phi 1 by d theta, and we've got our angle action representations of these things. So that's what that is, and that means that the change in delta on a time big T is clearly equal to this integral of the rate of change. And so if I want to calculate this second order diffusion coefficient, so with the page definition of it, I want to multiply the ith component of delta by the jth component of delta, both evaluated in time t. So it's an integral multiplied by an integral, which is a double integral. And so this double integral contains this. Sorry, yes. So we had this double integral, but then we're interested in the expectation value. Over the page, we had expectation value. So we're interested in the expectation value of this product, and what's random on the right-hand side are the phis. So we're interested in this double integral of the expectation value of these two things. When we integrated, oh yes, and there's another thing that's happened here, is we have the expectation operator allows us to average over the theta naughts, right? So this is theta as a function of time, and theta as a function of time is some initial value plus omega t. The initial values will be uniformly distributed. We're assuming that they're uniformly distributed in 0 to 2 pi, so we can integrate over theta naught. And when we integrate over theta naught, we discover that this integral vanishes. The integral vanishes unless k primed is equal to minus k. So that's what's happened down here. And we're left, of course, then with k dot omega. Both of these omegas are omegas, but we have a t minus t primed. So what we're interested in now is computing this expectation value, and we declare this expectation value to be ck, right? This is the definition of ck. And we argue that this should be a function of the time difference between t and t prime. There's no absolute origin of time in this problem. So there can't be explicit dependence on either t or t primed. This must depend on how much later t is than t primed. So we say that's on general grounds, ck must be a function of this time difference. We had a double integral. We were integrating over t and t primed. We would like this tau difference to be one of our variables of integration. Let's make the other variable of integration the thing called u, which is t plus t primed. And then, you do the ordinary change of variables, etc., on a double integral. And you wind up, the integral we were looking at becomes this. In other words, the exponential already depended on t minus t prime, I now call tau. Ck, we've agreed on general grounds, should depend on tau. So there's nothing left to depend on u. So we can just integrate this up, and we get we get 2t, right? And the half is gone. That's the t from the 2t. So we're looking at this. Now we say, well, we can probably allow t to become very large. It's sufficiently large that this thing has become small. We expect this to become small for the correlation to disappear for t minus t prime is simply huge. So we can identify this basically with the Fourier transform, the temporal Fourier transform of this function, evaluated at k dot omega. And the t goes away because this thing was the rate of was this product per unit time, and the time in question is t. So this goes away. So we have that significant result that this second order diffusion coefficient is connected to the power spectrum, the Fourier transform of this, which is sort of the power spectrum of the fluctuations. Okay, so what we've got is D2, because D2 was basically entirely this. The second order diffusion coefficient was just the thing we just computed. The first order diffusion coefficient, to get that, you've got to calculate this. We know we could work out what that is, but we don't know what this is. And the problem with this is that it vanishes. The expectation value of delta vanishes to first order, so you have to go to second order perturbation theory to compute it. And in an old paper with Cedric Lacey, in an appendix, we did this. But I'm not going to do it now. It's not a very instructive calculation. But what you find when you do it using this kind of apparatus is that it cancels its contribution to D1 cancels the contribution that you get from D2 when you take the divergence of this. So you end up with no D1. If you can also show, I've got as a problem in the book, that if time reversibility applies to the scattering process, it's another way of showing that it cancels. So it doesn't cancel. In order for it not to cancel, you need some extra physics, basically. A nice thing to do to convince yourself again that it in general can't cancel is to say, supposing f were the isothermal distribution, f were e to the minus beta h, where beta is the usual inverse temperature. We have sort of general grounds for believing that isothermal distributions, Gibbsian distribution functions, should be equilibria. That is to say that if we put this in, the flux should vanish. And the flux it's a very simple exercise to put this in and show that the flux doesn't vanish unless D1 is proportional to a suitable multiple of the divergence of D2. So that's that's left a bit hanging. It's worth thinking a little bit. I mean, there's a nice formula for the rate of change of the energy in the system. The E by dt is the integral of the energy, at some phase-space location, otherwise called h, of the rate of change of the number of stars there. But the rate of change of the number of stars is minus the divergence of the flux, right? Hence the minus sign, divergence of the flux. And we're doing an integral here. D6w can be written as d cubed j, d cubed theta. So here I'm doing an integral over j, so I can use the divergence theorem to move this derivative operator onto that when it becomes the frequency, omega. So we have this nice expression for the rate of change of the energy in the system. It's omega dotted into the flux. Now omega is the h is dh by dj, and no, I don't think I need. Yeah, okay. And then if I put this in for the flux, you see how well, yeah, this animal here is minus delta squared. Delta squared is manifestly a matrix with positive eigenvalues, and omega is in the opposite direction. Omega is dh by dj, so nh increases with j. So this, let us say that this is positive, then df by dj will be negative because the distribution function decreases with energy. So this is sort of df by dh by dj sort of thing qualitatively. So these two are pointing in opposite directions, and this thing has negative eigenvalues. So we have two minuses making a plus, and this term is going to increase the energy. And the role of this term is to drain that energy back out again. Yeah, so an externally applied, if the potential, unless the potential is generated by the stars themselves, you can show that D1 vanishes. I've already said that, actually. I think I've said all of that, right. And physically, you can see why the way in which, if the fluctuation in F is caused by an externally imposed fluctuation in phi through dynamics, the potential changes, it then steers the stars to new locations, then it's clear that F lags phi temporally. And conversely, if phi is actually created by Poisson's equation through F, then F and phi are going to be in phase. So you can see how the connection, which is the connection between F and phi, affects the sign of this autocorrelation. So let's do a different problem, which star-star scattering. So where P now of J and J prime is going to be the probability that a star with actions J is exchanges energy, momentum, etc., with a star on orbit J primed in amounts delta and delta primed. So J is going to go to J plus delta, and J prime is going to go to J prime plus delta. Right, so this is the probability per unit time of such changes. And then our bookkeeping is going to be that the rate of change of the stars at J is going to be a sum over all the stars it could encounter with, right? So this is a sum over neighbors, if you like, or other stars, times the possible changes that it could experience. And this is going to represent the stars moving in because we're going to have increments delta and delta primed, which are going to move J minus delta to J and J primed minus delta to J primed. So this is the stars coming in, and correspondingly, this is the stars going out because they're already there and they're going to suffer these changes, etc., etc. we once again Taylor expand. It's more complicated because we've got we can Taylor expand in J and J primed. So it's more complicated, but it's basically the same thing. And now we have to do a little bit of bookkeeping. One thing we will now do is take this d by dj. We can take a d by dj operator out of here, and then this first term is going to be fp delta. So here we have fp delta. I'm going to do some work on this. I'm defining h to be this thing which is differentiated with respect to j in this first term here. So this just repeats the definition of h. So time reversibility says that the rate at which stars at j plus delta go to, sorry, this is the rate at which, yes, stars at j plus delta go to j is the same as the rate at which stars at j go to j plus delta. So we pop that into here. We replace this with this longer thing, and then we change the sign of delta and delta primed, right? That's just a relabeling. So delta goes to minus delta, and delta prime goes to minus delta primed. And we pick up a minus sign in front there because this delta is changing sign. So we now have, we now Taylor expand this product, or this, sorry, this P. And the first term gives us back our original H, right? So the first term in the Taylor series expansion is P of J primed, blah, 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 which was what H originally was. So we find that H is equal to minus, that's that minus H, plus the derivative, you know, some terms. The first order, we're now keeping only the first order terms in the Taylor series expansion. Obviously, you can put this H on the other side and discover that 2H is equal to this stuff. We then take that information and put it back into the equation we had over the page previously. We find then that some things cancel, and we come down here. I don't think it's worth trying to do all the algebra. It's very straightforward maneuvering. We've got various derivatives and products, and we are able to cancel part of this cancels on one of these, and then we're able to clean things up. So we end up with an expression for the flux, which again we arrange like a coefficient of f and a coefficient of the gradient of f, where the coefficients are quite straightforward things. And the point I want to make is that in this case, we have our calculation has yielded D1 and D2. They're both specified by whatever this probability is. Now, to go further, we need to actually calculate what these probabilities are, which means we've got to calculate the probability that a star cruising along experiences a change delta and that kind of thing. So that's what comes next. So what we're going now to allow for the possibility that the stars the interaction between stars, because it isn't occurring in vacuo, it's occurring in the polarizable medium provided by the other stars, has some dressed potential. So psi is of JJ primed is simply the potential experienced at J theta as a result of there being a star at J primed theta primed. So that potential in vacuo would just be GMM over x minus x primed, but we're not restricting ourselves to that possibility. We're saying, you know, let's allow for the fact that there is an entourage of stars around the star at J primed, theta primed, which enhance its effective mass. So this object can clearly be Fourier expanded in the angle variables. And then Hamilton's equations give what they give, you know, rate of the derivative with respect to, and here we have an m primed because because psi doesn't contain any masses. The definition of psi is actually g over x minus x primed, as it were, in vacuo. So it doesn't contain any masses, and therefore I need to multiply by the mass of the prime star in order to get the acceleration that it causes to the unprimed star. And ditto, primed thing is being pulled by the unprimed thing, and so the mass of the unprimed thing needs to go in here. We integrate these things up, right, over some time big T in order to get the change. We multiply them together. Now, this is all I say these things. I'm actually only working with this one, not using this one. So I integrate this up. I multiply on itself. It's basically the same thing we had before. And then I take the expectation value. So it's very similar to the previous calculation. I have these theta naughts. When I average over the theta naughts, I find that k, this is clearly going to average to nothing unless k is equal to minus q. And this is going to come to nothing on averaging on theta primed unless k primed is minus q primed. So that's going to happen. And I guess that's about it. So that brings me to here, where that used to be a q, and that used to be a q primed, I guess. And then we know that because psi is a real function, its Fourier components associated with negative indices will be the complex conjugate of that with respect to positive indices. In other words, this product is just the mod square of the complex number. And we have this thing. And as big T goes to infinity, it's a sort of exercise in contour integration to show that this thing goes to delta k plus k dot. It goes to delta of x, basically. This thing goes to delta of x. I hope you can sort of, it's very similar to things you've seen with sinc functions as time goes to infinity, but it does a little bit of contour integration persuades you that that's the case. So we have this, and similarly, you know, so that we've only calculated that one, but you can imagine that calculating the other one is practically the same thing, and it comes to this. All that changes is that k becomes k primed, and we stick those into our previous formulae, and we get this. So here we are. We've computed the diffusion coefficients now, if completely. It of course depends on what you take to be the dress potential. You could just put in the Fourier transform of 1 over x minus x primed here to get the vacuum version, whatever. Something which, an aspect of this which is significant, is that the first order diffusion coefficient involves m primed, and the second order diffusion coefficient involves m prime squared. In other words, this diffusion coefficient is proportional to the mass of the star, which is at J, but the second order one isn't. It depends only on the mass of the star, which is at J primed, which of course is summed over. So what does that mean? It means that the heating term, right, the term that causes diffusion to ever higher actions, is independent of your mass. It depends on the mass of your neighbors because they're shaking you, whereas the friction term, the term that's dragging away your energy, is proportional to your mass. So if you consider the effect of this diffusion on a massive star, it's going to, relative to the effect on a low mass star. A low mass star is going to be shaken, whatever, and it's going to feel a drag, but the drag will be modest. And so these two terms will come into equilibrium at large J's. Whereas if you have a massive star, it's going to be shaken by the same amount as the low mass star, but it's going to experience a drag which is m over m times bigger than the low mass star. And so it's going to be dragged back to low actions. And so that's the origin of mass segregation. That's equipartition. That's statistical physics driving equipartition. It's pulling massive stars to the bottom of globular clusters or whatever. All right. Star wave interactions. So, as I tried to explain yesterday, the phenomenon of particle dressing, of which we'll say more later, implies that there is the possibility that there is energy and momentum in transit between stars in excitations, collective excitations of the star field. And we ought to consider, we should consider this energy that's in transit. So in a disk, this wave field is extremely obvious. It is spiral structure. You can see it. In a globular cluster, you can't see it just like that, and it's probably a lot less important, but you have reason to believe it's there. The concept of a wake, the concept of an entourage around a star tells you that it must more or less be there. All right, so stars is the way we're thinking about this now. So in a sort of electrostatic world, we imagine that particles interact with each other directly. And then we move on to electromagnetism, and we recognize that actually nobody talks to anybody directly. It's not allowed by relativity. Each charge talks to the electromagnetic field in its neighborhood, which then, in other words, it launches waves where it is, which pass to the speed of light to other charges, and those waves then accelerate those other charges. So this acceleration of a star that I've been talking about, I'm saying a star is being shaken by its neighboring stars. I'm now saying, no, forget that. That's kind of high school physics. The real thing is that the distant star shakes the star cluster, launches a disturbance which arrives at me sometime later and causes me to shake. And then, of course, I shake and launch waves, which so we have this idea that every star is absorbing waves and is emitting waves, and it's through this wave field that these are all relevant interactions are happening. Now, stars are stochastically accelerated by the wave field at a rate that must be proportional to the energy density in the wave field. But the loss of energy to the wave field, we're going to persuade ourselves has terms which are independent, so depend on the naughth power of the energy in the wave field, as well as a term that's dependent on the first power in the wave field. And that is similar to, that's analogous to spontaneous and stimulated emission. So stimulated emission and absorption is clearly proportional to the energy density in the wave field, in the EMAG field. But we know that atoms have a probability spontaneously to decay. So even if there's no energy in the wave field, they can still decay, putting energy into the wave field, right? And the same thing applies here, although this is all nothing to do with quantum mechanics. So what's the change in the energy of a star when it suffers a change in actions delta? Well, it's m delta dH by dJ, right? Because I mean that just says the change in the energy when we change the actions, because this is the change in the actions. So that is m dot omega, right? That's the change in the energy of a star when it changes its actions by an amount delta. So let's ask about the change in the energy of the wave field as a result of all these goings on. So that's the integral over all the changes and actions that are happening times the energy that change associated in that. And here we have the stars which are absorbing energy, right? So these are the stars which are being promoted by delta from J. So we need a minus sign here because this is energy drawn. This is the energy drawn from the wave field. And these are the stars which are being demoted. They're suffering changes in action minus delta. And so they're giving up their energy to the wave field. Now, reversibility says that the rate at which this is going from J plus delta to J, that should be the same, that should happen at the same rate as going from J to J plus delta. And if we put that in here, we arrive at this conclusion here. This is obviously looking like d by dj, delta d by dj of f. And then that the d by df can come out, the delta stays in, and so we have this. And this integral we called delta bar squared or something, and then we define this to be minus a half of delta bar squared, and so we end up looking at this. So the energy, the rate of change of the energy in the wave field is simply equal to this, which agrees with the energy gained by stars when the drag field vanishes. So we've done stimulated emission and absorption, but we haven't done spontaneous emission. So if you ask about, so what we know is the rate of change of the energy of the stars. I showed that it was equal to this integral, and then replacing the flux, we already had that formula. So there's a part like this, right, with an opposite sign to that, as we expect. That all drops out automatically without any stress. But we also have this term here. So what is this term here? This is, as I say, a loss term. And for consistency, this loss term has to appear in the energy equation of the wave field. So the energy equation of the wave field should really be this, right? In order that these energy is conserved. Now, consider the case, right? We know that D2 is proportional to curly E. We've argued that on physical grounds. So if you accept that that's true and look at this equation in the limit that the wave energy is very large, then D2 will be very large. This will be this coefficient curly D that I defined over there times curly E. So if curly E is large, this term becomes more important than this term, and it's talking about exponential decay at a rate, this rate. So what does that say? That says that in some kind of classical limit, right? So ordinary electromagnetism is done in the limit when spontaneous emission is unimportant, because there are gazillions of photons. The energy in the wave field is large compared to h bar or whatever. And so in this sort of classical limit of a very highly excited system, the wave field should decay with this rate constant. And that is conventionally called the rate of Landau damping. And I've decided not to discuss that there, because time doesn't allow. But it's kind of interesting that there is this connection between the rate of Landau damping and the diffusion coefficient per unit strength in the wave field. All right. So would this be the moment for a breather?
I guess.
Yeah, I guess so. And any questions?
And that numerical simulation of these stochastic processes.
Yeah, some have been done by well, okay, so what should I say? What should I say? There is a huge literature on the stochastic scattering, two-particle scattering in globular clusters. And the big question there is, what is the role of self-gravity? Is self-gravity actually important? And that's still a little bit controversial. There is a paper by Fovry et al. In 2015 and a few follow-ups about how this all works out in disks, like in our own stellar disk, like in our own galaxy, where it turns out that the self-gravity causes the relaxation to happen, say, 100 times faster than the numerical experiments are, I have to say, not entirely satisfactory still, for sort of technical reasons that so a big issue in spiral in disk dynamics is so what this formalism is telling us. Well, I haven't quite. We're going to get to a formalism which makes it clearer. Is that it's telling us you should think about the stars as being oscillators or groups of oscillators, and they're talking to each other. And they're all emitting radiation and they're all absorbing radiation at particular frequencies. And it's a very important question to what extent particular frequencies play a role. And these disk dynamics simulations tend to indicate that, provide evidence that there are particular frequencies which are causing rapid diffusion, which means that you develop features. You start with a smooth distribution function, and then stars are accelerated. Stars, and all at fairly low radial action, and then because there are particular frequencies favored by the system, stars at a particular radius or with a particular angular momentum, which resonate with that, get particularly strongly accelerated. And the question is whether it's undoubtedly the case that in these experiments there are particularly favored frequencies, but is that a realistic thing, or is that something that arises because of the way people set up the simulation in the first place? You have to do something. So a sort of very large scale disk is just plain unstable. With realistic parameters, is just unstable to collective motions, and you kind of stabilize it by depriving it of its self-gravity at small and large radii. And that introduces characteristic frequencies, and there's a danger that what we're seeing is that. Don't think that's a very satisfactory response. I think that's, however, reflects the fact that there is a people in Paris have done quite a lot recently on globular clusters in this context, and the conclusion there ultimately is that the self-gravity effects are not very important, and at the end of the day, the diffusion is dominated by the two-particle effects. But my perspective is that it's not so much. The big question is, to what extent a self-gravitating body has macroscopic fluctuations at very low frequencies. So we'll kind of come to that in the periodic queue, but it does have favored frequencies, and at which it has oscillations which require relatively little energy to excite, and therefore in the statistical sense will have large excitations. And I think in the case of a globular cluster, these happen at frequencies which are too low for stars to resonate with them, which is actually probably why they get to have significant excitation. And I think in-body experiments see those excitations, but it's not well documented or it's not properly pinned down at this time. And the question is whether you could see that in real globular clusters, for example. I think you should be able to, but I don't know of anybody who's really seriously looked. Maybe I should just go on. Or are we going to
I think
freak out?
waiting outside, there was the
Right, okay. Okay, so in order to make progress, we need to solve this equation. This is the linearized collisionless-Boltzmann equation written with angle action variables. We have to solve this bearing in mind that these two are coupled inter alia by the Poisson equation. And to do that, we take advantage of bioorthonormal potential density pairs. So I'm just going to introduce those for a moment. So we imagine, well, we don't imagine, we insist on having a family of functions rho alpha and the corresponding densities phi alpha, so that these potentials, this is a family of potentials, the basis functions and basis functions in density, which are coupled by Poisson's equation. And we're going to suppose that there's sort of orthonormality to these things in the following way, that if I take the complex conjugate of this and multiply it on that and integrate over real space, I get either minus epsilon in the event that these belong to the same pair, or I get nothing when they don't. We'll see some examples of this a bit later, probably tomorrow. That being so, suppose that, and these are basis functions, that means that any density can be written as a linear combination of them with some expansion coefficients A alpha. It's immediate then that if we have once decomposed rho into its numbers A alpha, then we've got the corresponding potential. So solving Poisson's equation then becomes trivial. You just replace rho alpha by phi alpha and vice versa. And bearing in mind this orthonormality, we can figure out that A alpha can be obtained out of this by multiplying. If we multiply rho by phi star and integrate, we will get out to within a factor of -1 over epsilon A alpha. I should just say something about this epsilon or curly E thingy. Most people who work in this field traditionally, they say this is just minus delta alpha alpha primed, but that leads to all kinds of dimensional difficulties. This commodity here has units of potential per unit mass times mass, therefore it has the units of energy. And that's the role of this epsilon thing, is to deal with the units of energy. I can't bear to work with sort of where it isn't apparent what the units of everything are. Right, but most people leave this out. Okay, so yes, and now if you ask what is the relationship, so phi is equal to A phi alpha, right? So an A is equal to this. If I put those together, I find this relationship between phi and rho. But we know, of course, that phi and rho are related to each other by Poisson's integral. It's the integral dx primed of g rho over x minus x primed. And so comparing this expression with Poisson's integral, you come to the conclusion that what you've got here, this matrix, or this operator, this integral operator, because it's a function of two things, x and x prime summed over alpha, this thing is the matrix representation of that function g over x prime minus x. So we'll use that fact from time to time. What else can we say? A alpha is obtained by this integral here, but rho is an integral of f over over velocities. So, and then the integral dx d velocity can be written as dj d theta, and I can, and if I'm doing angle action coordinates and I've Fourier composed everything, I can do the integral over the angles. So it's also true that this a perturbation, a distribution function, which has angle action component fk, generates a alpha like this, right? So we can go straight from the distribution function to the expansion coefficients of the density or the potential using that thing there. Another interesting thing we can do is we can work out what the potential energy is, the integral of an arbitrary potential times an arbitrary density with a factor in half in front is the potential energy of is the self potential energy of that density distribution. And phi is a real function, so I can put star on it. I can complex conjugate it without consequences. Then I can expand it, do the integral, and we arrive over here at the mod square. So if you add the mod squares of the A's within a factor of E and a half and stuff, you're getting the potential energy. That's what those things are telling us, that's another fact we will find useful. So we're doing, you know, we're doing small perturbations. We've got these equations describing how fluctuations in the distribution function propagate through phase space. An obvious thing to ask yourself is, well, so what's the energy of this fluctuation, right? So we've got a fluctuating thing, this. What's its energy? Well, to work that out, it's exactly analogous to the way you work out the energy of an electromagnetic field. When you work out the energy of an electromagnetic field, you say, let me set up that electromagnetic field by dragging a charge through the field, building it up. So that's what we're going to do here. We have got an external potential phi e, that's what we do the dragging with. That's going to provide a force, mass times minus the gradient of phi e, and that's going to be doing work at a rate, the mean velocity of the stars, this is the expectation of the velocity, times the mass, right? So sorry, this minus phi e is going to provide an acceleration. You need to multiply by the mass in order to get a force, multiply by the velocity, and you've got a rate of working. Then add that up over all the places you're doing your work, and this is the rate at which you're working, and with proper bookkeeping minus sign. So this is going to be the rate of change of the energy of the distribution function. And yeah, we've got a position integral, a velocity integral. That means we've got an integral over phase space of this. We also know that v dot gradient can be written as v is dh naught by dv. So this is dh naught by dv d phi by dx, which is minus this Poisson bracket. And this Poisson bracket can be evaluated in angle action format when it becomes dh by dj d phi by d theta, and hence this with appropriate change of sign. So let's replace that with that, and we're here, and replace this with d cubed theta d cubed j, and do and expand these in Fourier components and do the theta integration, and we come here. Okay. So this is the rate of change of the energy after some maneuvering. The collisionless-Boltzmann equation says this. We put this to 0 before because we were considering fluctuations, free oscillations of the field, but now we've got an external component of the potential. So I've got an S here on the phi, which indicates that's the contribution of its own density to the potential. And here's the externally imposed potential. So this is the collisionless-Boltzmann equation with the potential divided into a self part and an external part. And now we eliminate phi e between these two equations and discover that dE by dt is this. Right, horrible. The thing to say next is that this middle term is going to contribute nothing because we're summing over k. This fk star means that this this could be written as f of minus k, and then this product and this product is then invariant under k goes to minus k, but this is changing sign onto k goes to minus k. This is invariant onto k goes to minus k because we get minus signs on top and bottom. So there are equal and opposite contributions from this term, from k and minus k, so we can drop it. Then we can say that bearing in mind that this is f of minus k, and we're summing over all k, we can combine this and this. We can say this is d by dt of fk mod squared half. So that and then we can take the derivative out, and we discover that the first part can be written like this. So it's the rate of it can be written like this, which is the rate of change of the kinetic energy. Well, the crucial point is I can take this t out, this d by dt operator outside. This is unperturbed. The only thing that depends on time is this. So this d by dt can come outside, and we're talking about d by dt of a thing k, which is defined by everything else, which on physical grounds we identify as the kinetic energy. So the last term, this back term, we can also maneuver into a total derivative with respect to time. It is a little bit, it requires a few extra steps, and I decided not to go through with them, but we can show that this last term, we can maneuver it into d by dt of this lot, which is manifestly the rate of change of the potential energy. So adding these bits together, we have that d by dt of k plus d by dt of p is equal to dE by dt, from which it follows, the expression for E follows, right, as this bit, which must be the kinetic energy, because this is clearly the potential energy. So this is quite interesting, that this is the kinetic energy, right? It doesn't look like it, does it? But it clearly is, and we will use it. If we write this in terms of potential density pairs, the potential energy, I already said, the potential energy can be written like this. So it looks like that, and that formula will recur quite soon. That is the form of the energy. That's a way of writing the energy of a disturbance. Okay, so now I'm going to talk about normal modes, because they are, in any ordinary branch of physics, given a field or a dynamical system, what do? We consider small disturbances, and we consider the case where everything goes around sinusoidally. So f of j and t should be f of j with the parameter omega, e to the minus omega t, ditto the potential. And we stick this into the linearized Boltzmann equation written in angle action variables, and this is what we get, right? With the d by dt has become we already had a spatial derivative d by d theta, which gave us an ik something or other, and then we've got an I omega coming down from the time derivative, and on the right hand side we have this. Now the key point that Van Kampen pointed out in the 1950s in the electrostatic context is that this that is on the right hand, in principle, everything here is proportional to Fk, right? Because this is the self-gravitational potential. It's a linear functional of the Fks, but this depends on J, that depends on J. This thing over here depends on all of the Fks and all of the Js. So if I'm looking at this equation and asking myself, what is Fk of a particular value of J? I can treat this on the right-hand side as a given, because if I change Fk of J by even a large amount, there'll be a negligible change on the right-hand side, because this thing depends on all the others. So effectively, when k dot omega is not equal to little omega, then we're discovering that some multiple of Fk is some basically determined object on the right-hand side, and we can just solve for what F is by dividing by this on that side. And when k dot omega is equal to little omega, this equation says that naught is equal to the right-hand side. So we learn nothing about F of k. So it's it's very different from the ordinary normal mode system where we have some matrix A on X is equal to A on X is equal to B, and sorry, well, usually is equal to, let's keep it simple, where we now say this is A minus I X. Well, I usually have a lambda here, so whatever. Anyway, but usually what we say is that this only has solutions when the determinant, when this is a singular object, right? And we say the determinant of that has to vanish. Here, we basically have an inhomogeneous. Yeah, sorry. What's really happening here? The analog here is that something or other on X is equal to something or other. And so long as this thing is non-zero, we can say that X is equal to A minus 1B. We're all done. And that's basically B in this context is this right-hand side, which barely depends, effectively doesn't depend on FK. That's the crucial point. And so I can just do this division. Now, if, on the other hand, so this is good, except when omega is equal to this. And so there's a P here for Cauchy principal value put in, which says, okay, this is the right thing, but leave out, this doesn't apply in the case that omega is equal to K dot omega. Just forget it. When this thing vanishes, this equation, as I've already said, actually doesn't constrain FK. It doesn't tell you anything about FK, does it? So you're allowed to, at the value, in the case of omega, you can make this anything you damn well like, because you're going to multiply it by 0, and so you'll get 0 whatever you put. So this term says that when omega is equal to K dot omega, you can declare this thing to be whatever you like. So this is an arbitrary function at our disposal. And this is the distribution function of a mode of a stellar system, usually called a Van Kampen mode, but I dislike the fact that's sobriquet because it implies that that's some kind of special mode. This isn't a special mode. This is the mode. This is there is no other, this is it. Okay. Now, GK is arbitrary, but if you change GK, you're going to change this phi here, and let's figure out what that is by multiplying by d6 omega easily multiply by this and integrate. And then on the left side, we get this, right? So we're going back to this equation. We're going to this equation here with considering the right-hand side to be G. No, the right. Yep, sorry. What's happening here? Yeah. We're writing this as D6, as D3 theta, D3J. We're doing the theta integration. This, of course, is a function, excuse me, yes, that's right. So what's happening here is that this is a function of X, and I'm Fourier expanding it in e to the I k thetas, etc. So this here, sort of sub k, which means implicitly it's a function of J, and I am integrating away. So and I get this is going to. This involves a sum in principle. When I Fourier decompose this, it will be a sum over k primed, e to the minus I k primed minus because of the star, and it's this integral over theta is going to vanish unless k is equal to k primed, and so we end up over here with a 2 pi cubed from when the Fourier terms match. So that's the left side. On the right side, we take this, we've multiplied it by this garbage, and you work away, and you wind up with this. And then, oh, that's for the first term. And then for the last term, we've got this. We gather everything together. That was the left side. That was the first term on the right. That was the second term on the right. Now we sum over k, and then the left side becomes simply minus a alpha, right? That's not obvious, but if you refer back to the previous formula, you'll find that that's the case. The first term on the right becomes a matrix times a alpha. You can sort of, well, here is a alpha, right? So then there'll be a load of stuff multiplying the a alpha, and the load of stuff multiplying it is this. So this is just some numbers that depend on omega from here, and they depend on alpha and alpha primed. So we're going to call this m sub alpha the response matrix. It's something which depends on the unperturbed distribution function and the basis functions we're using to expand our potentials in. But given all of that, it's a well-defined matrix. So the left side being linearly proportional to alpha can be written like, sorry, the right side, the first term can be written like this. We move, so on the left we've got A, on the right we've got A, so of course we move the M to the left and define ourselves P alpha, alpha primed alpha, which is the identity operator minus this, and then the left side becomes that times A is equal to the right side, where B alpha is this integral over G. So this is essentially arbitrary because we said G was essentially arbitrary. But whatever it is, it controls A because P is a well-defined matrix. And most of the time it's going to have an inverse. And so we're going to say that A is P minus 1B. So what are the B's? The B's are clearly the expansion coefficients. They're simply the representation in terms of basis functions of the density which is generated by the G's. Now let's just think about these G's. G only matters, it only matters when it's the density on a torus which has a resonance with the mode, right? So it doesn't matter what you put for this except when k dot omega is equal to little omega, the frequency of the mode. So it is what it is it's a distribution of stars, a non-trivial distribution of stars because it's got k in it, right? Which means it's a distribution of stars that's sinusoidally varying over the torus J, which evolves in time at the same frequency as the mode, which is probably a better way of expressing it than resonates with. So the point is that if there are certain toruses which have k's, so that k dot omega equals omega, and supposing on one of those toruses you put in a pattern e to the I k theta of stars, then if there was no gravity, no self-gravity, as those things just followed their unperturbed equations of motion over the torus, they would generate a density which was fluctuating at frequency omega, and they would do that forever. So these arbitrary functions G are describing possible wavinesses on toruses such that you can get so that the density is fluctuating at the frequency omega which you have chosen for the mode. And what is A describing? Well, A is describing the density of everybody, right? That's because A is describing the potential of the whole system. So these stars which are oscillating on these special toruses, which are capable of supporting a pattern that oscillates, a density profile that oscillates at frequency omega, their gravity is inducing in other stars which don't resonate. They don't, on other toruses that don't resonate, it's inducing fluctuations at frequency omega, and A is describing the potential that is produced by the resonant stars on that are described by G, and all the other stars. Right. So this term here is talking about the steady response on other toruses. Here's the sum over other toruses to the driving force coming from here. And that response, surprise, surprise, becomes large as the frequency on that torus drifts towards the frequency of the mode. So the response becomes large. There's a P operator here, so we never allow omega to become equal to K dot omega. So it rises as we move towards a resonance. Then this stops, and we have this very large response. So this is totally coherent. This is the driven response, which diverges as we approach the driving torus. On the driving torus, it's not even finite. And then, of course, as we go on the other side of the resonance, it falls away again. So that's the physics of these modes. Right. Now, a really crucial and absolutely crucial point is that you can find a normal mode at essentially at every frequency for which a torus is capable of oscillating, right? So in general, the frequencies vary as we move through action space from very low values, characteristic values at high frequencies, at large actions, sorry, to a maximum frequency which is achieved in the middle of the stellar system. And those are sort of base frequencies, and then you can also consider multiples, integer linear combinations, K dot omega, made out of those basic frequencies. So we have basically a continuous, we have an enormous range. It's not necessarily an infinite range, but we have a very large range of frequencies at which you could find a torus that will do this trick and drive oscillations, and therefore we have normal modes at a continuous spectrum of normal modes. This is completely reasonable because one of the things you would like to do with a normal mode is use it to represent initial conditions. So we all know that with ordinary oscillating systems, we can take any initial condition, write it as a linear combination of normal modes, evolve the normal modes by multiplying by e to the minus I omega t, reassemble. This is how we do quantum mechanics, right? We find the stationary states, those are the normal modes of the Schrodinger equation, evolve them with e to the minus I omega t, reassemble, and we've solved the time-dependent Schrodinger equation. But we do it also with mechanical oscillations, etc. So you have to have enough normal modes to describe your initial conditions. If you're doing the initial condition, if you're discussing the sun, which is a kind of an oscillating system, it has a discrete spectrum of normal modes. So there are an infinite number of normal modes, which is a countable infinity of normal modes, and that corresponds to the fact that in order to specify an initial condition of the sun, I've got to specify the density and the velocity at each point in the sun. If I have a globular cluster, which is a bit like a sun, right? But in order to specify initial condition, it's not good enough to specify just the density and the mean velocity. I have to specify a whole velocity distribution all over the place because I don't have any. The sun is relatively simple because I can argue that the velocity distribution everywhere is Maxwellian. I need two numbers to define it. Well, 3, 4 maybe. I need a mean velocity, so that's three components of velocity, and I need a dispersion velocity, the temperature. But it's not like I need much more information to specify the state of a stellar system, and that's why there are more normal modes. That's why there's an uncountable infinity of normal modes. Now, it's useful to define an inner product on these fluctuating Watsits, and we define it like this. And this is a formula you've pretty much seen before. When f tilde was just equal to f, this was the expression for the energy associated with f. This was the kinetic energy, it was mod f squared, and this was the potential energy, a mod squared, right? So we define an inner product being a bilinear thing, as you see this bilinear thing, because the A's are linear functions of the F's, so that the mod square of something gives you the energy. Under this inner product, you can show it's quite a tricky calculation, but you can show, and you can find it in a paper by Lau and me. You can show. Sorry, there should be a prime on this. You can show that the inner product of two normal modes is orthogonal in this sense, that if I take an f of omega and an f of omega primed in a product, I get nothing unless omega equals omega primed. And then I get a delta function times some number. The reason it's a delta function is because because these things contain delta functions, and that's why sort of this inner product is sort of divergent. Always, because the spectrum is continuous, when we use the normal modes, we will always be integrating over omega, and therefore these delta functions will go away. So they're not a cause of stress, but they are a bookkeeping issue. So what is this orthogonality? Means that the energy associated in normal modes is additive. If I have a disturbance which is written as a sum of normal modes, right? F omega is the wave function of a normal mode, and A omega is the amount of it we need, then the energy of that disturbance is going to be, you take this and stick it into that formula, it's going to be this, and so we're going to do this integral, blah, blah. That will generate, when we integrate, that will give me a delta function. I will do this integral and I'll conclude that the energy is the sum of the weights of the individual normal modes squared times the energy associated with unit normal mode. And it's another key property of normal modes that we value in the ordinary world. Okay, so now I'm going to talk about modes and Poisson noise. So suppose we are starting an n-body simulation. The way we do this typically is we're doing a simulation of some equilibrium model F naught. We start it in some interesting equilibrium model. So we sample this statistically and get a load of particle coordinates theta I, j I out of our random number generator, and then we can consider that the distribution function we start with is this Klemontovich beastie being a sum of delta functions, right? There's no particles anywhere except at theta I and ji. So that this is equal to this Fn is not the same as F naught. Clearly, it's not the same as F naught. It is, in fact, F naught plus a perturbation, which is this thing here. And this perturbation has non-vanishing expectation value, and this is what I want to work out. So we want to know what this is. You'll see why we want to know what this is going forward. And it's clear, you multiply these two together, it's clear that these terms vanish because this is the mean value. No, hang on a moment. Sorry, the mean value of Fn is F naught. Sorry, these don't vanish at all. We get minus twice F naught from this and from this, and then we get plus F naught from this and this, and so at the end of the day, this is what this expectation comes to. It's the expectation of this product of Fn on itself minus F naught, and then when you work out what this expectation is, it's a bit fiddly. Don't think we should go through it. It's not rocket science. You come to the conclusion that this thing it has two terms, as an F naught again, which arises from, when we work this out, we're basically doing a product of a sum over particles and a sum over particles, and we break that down into two parts. The part where theta I is not equal to theta j, right? The non-diagonal parts of the sum, and plus the diagonal parts of the sum. Not surprisingly, they give different answers, and this part comes from the non-diagonal part, and this part comes from the diagonal part. So then when we plug this expectation of FFFN into our formula for F1, which is what we really want to know, we get sort of just F naught times some deltas, but we also get an F naught term. And if the next thing we do, we would like to know what this looks like in terms of Fourier components. So we Fourier expand this, we Fourier expand this by multiplying this whole thing by e to the I k dot theta, e to the I k dot k prime theta primed. And the relationship we have between the Fourier components is looking like this. So this is a really important relation. Okay. So in the absence of gravity, the distribution function of a mode reduces to the GK, right? In the absence of gravity, M, the matrix M, vanishes, and P, which is 1 minus M, becomes just 1, and there's nothing. Well, in the absence of gravity, it's clear that the resonant torus can't excite any other torus, and so the whole density, the whole distribution function is G. And the Klemontovich distribution function that you've got is the distribution function that you would keep if you advance the particles in the mean field model rather than in their self-consistent potential, right? Because if the particles can't see each other, they just move to new locations in the mean thing, and that's a distribution function you could have obtained by doing random sampling. So the Klemontovich distribution function is a normal mode of the system in the absence of gravity. So well, I say it's a normal mode. It is a sum over frequencies. So if I ask myself, what is the expectation value of the distribution function squared in this Klemontovich thing, from the normal mode perspective, it's a sum over normal modes, all the normal modes I need to represent. I said the Klemontovich was a normal mode. It isn't. It's a sum of normal modes of the gravityless system, and this integral gives me the integral over because G times delta is the distribution function of a normal mode. So I'm multiplying distribution functions of normal modes and summing over frequencies, summing over normal modes, and that must give me the same thing as I've just worked out is the expectation value of the Klemontovich. So this is the expectation of Klemontovich worked out using normal modes. This is the distribution of the expectation value of Klemontovich worked out by hard slog in traditional ways. So right, you'll see why this matters. Now, when you advance the particles in the self-potential, you find that dressing of particles becomes important because the Klemontovich isn't. Let's not try and explain that. So now what I want to do is compute the contribution. What am I trying to do? I'm now focused on computing this expectation value, because this is what drives the diffusion, right? I think early on, saw that the flux was given, basically was the divergence of this thing here with respect to J. So I want to compute this and how using these normal modes. So I say, let's consider the contribution of one mode to this interesting thing. We'll add them up over frequency later to get what we want. So this is phi, and here is the distribution function of a normal mode, right? Complex conjugated. And we have two terms, and one term is this stuff times phi k star. All the randomness is in here, so the expectation value has gone down there. And the other one is phi k gk, and there's a delta function. Now phi k, we've already seen, so we can expand it in basis functions, and A is P minus 1 of B. B, remember, is an integral over G. So that's what this says down here. This is just saying that phi is the potential generated by the whole thing, which is P minus 1 on the density that G generates. We can identify all this stuff as being E. Now, what is this operator E? E is really the action angle space representation of the polarization, or the inverse of the polarization operator P minus 1, right? We're multiplying an operator by a basis function on the left and a basis function on the right, and summing. So all we're doing is moving to a new basis in which to describe this thing here. So that E is a sort of primitive object, is determined by the unperturbed system. The physics of the unperturbed system is encoded in P minus 1. These basis functions are just arbitrary choices. So this formula looks awful, but it's not that bad. So it is the inverse. This is just a way of writing P minus 1 on G. So that's the potential. So now I've got the potential. I'm trying to work out this phi G expectation value, but now I've got an expression of phi as a multiple of G. So when I put this expression into here, I'm going to be taking the expectation of G times a delta function times a delta function. But that's exactly what we just worked out. So we're going to want this is going to, that's right, this is going to be this product. But we know what this product, well, when integrated over omega, so if I now integrate, this is the contribution from one normal mode to part of the flux. When I integrate over omega to sum over normal modes, I'm going to be integrating this with respect to omega, and then I can use my Klemontovich expectation value to find that it's this. And so that's going to give me one contribution to the flux, which looks like this. And the other contribution to the flux is basically the same thing. It depends on, there's this thing times the phi k star. Both of these get to be expanded in terms of G's. This is equal to, roughly speaking, EG, and this is equal to E star, G star. Here's the E, here's the E star, here's G and G star. Again, we want the expectation value of this integrated over omega. So we integrate this over omega to get the contribution from all possible things of that product. And this is what it comes down to be. And we have some delta functions, which mean that this thing becomes the complex conjugate of this thing. So the mod square of this is what appears. So that gives me a coefficient here of the gradient of F naught. So this is the second order diffusion coefficient, where the second order diffusion coefficient is everything here except that. Now, when you first look at this, you think, oh no, this is clearly real. I mean, it has to be real. And this integral is extremely real, right? It involves a mod square, real, 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 real. Everything's real. And right in front here, we have an I. So your first thought is, oh no, need to check the algebra. But no, let's think about this. What is this describing? It's describing the rate at which sort of energy is being put in from J through into an oscillator that sits at J by oscillators at J primed. And here are the frequencies of the relevant oscillators. So let's think about the rate at which a force driving an oscillator, we'll stop after this, force driving an oscillator does work, just an ordinary, boring, damped, simple harmonic oscillator. And let's consider the limit as the dissipation goes to naught. So it's kind of first year undergraduate work to show that the rate of working of so I've got a damped harmonic oscillator that I'm driving steadily. And the rate of working, it turns out to be this, alpha plus and alpha minus are the normal frequencies of this damped oscillator. So believe me, it's this, and the K, sorry, here is the damping rate, is the coefficient of damping in the oscillator. So we end up with this. And what we want is the integral over frequencies, because let's suppose we now drive it. So this is what happens if you drive it at one particular frequency omega. But suppose you drive it at a range of frequencies. So then we want the rate at which it's dissipating energy summed over frequencies. Then it works. You can show by complex integration it comes to this. And as K goes to naught, K is the damping in the oscillator. As K goes to naught, you can see that this doesn't go to zero. It goes to a well-defined non-zero number. So what's the point? The point is that the limit. So we are modeling in this calculation, we're modeling our stars as undamped oscillators, but we're talking about the rate at which energy goes from one to another. And that's slightly inconsistent. We have, in order for energy to go from one place to another, we need for there to be some notion of damping. And so what we need to do is make k dot omega, which is the frequency of the driven oscillator, just infinitesimally have an infinitesimal positive imaginary part, which would correspond to it being an infinitesimally damped oscillator. That done, it's easy to show that this becomes a pure imaginary number when, in analogy with this, and we wind up with this formula here, which was achieved by Chavigny in 2012 by other means, by Landau apparatus. So let's leave it at that. What I've hoped I've communicated in the second lecture is that stellar systems have normal modes at more or less all frequencies. The dynamics of the reason for this is sort of physically apparent in terms of how much you've got to specify in order to specify initial condition. Something I didn't say that I should have said is that it explains why these systems have sort of dissipative phenomenology. If you jog a stellar system, it oscillates for a bit and then the oscillations die down. It looks as if it's being damped, even though, of course, it works according to time reversible equations of motion. And the reason for this is precisely this continuum of frequencies. So you can't excite a single mode at all. It's a logical impossibility. You always excite some range of normal modes, which have cover some finite range in frequency, and the amplitudes of these normal modes evolve because they evolve at slightly different rates. They gradually become uniformly distributed in phase, and the damping time is the time it takes for them to spread out from some particular phase to 2 pi. And by this Klemontovich type argument, we can discover what the autocorrelation is of these G functions, and then using those, we can calculate the actual fluctuations in Poissonly excited systems, even when there is self-gravity. And I've concretely used that to derive the first order and second order diffusion coefficients of a system when self-gravity is taken into account. So the agenda tomorrow will be to talk about the application of this to the periodic cube, which is a toy model for which all of these formulae can be deployed in a practical way, and you can do simulations of. Okay, thanks, folks.